Swayam Prabha. Digital India. Educated India.
Welcome to the 29th lecture in Mechanics of Materials. In the last lecture, we began looking at members subjected to a twisting moment or torsion. In particular, we looked at the effect of twisting of a closed section. By closed section, we meant that it won't warp. We will see in more detail what warping is and how do you analyze for structures that will warp and twist it in this lecture. Basically, we said that two surfaces because of twisting will rotate relative to each other and there will not be any out of plane displacement like this. Okay. So, basically with that assumption we came up with the displacement field. We said that the displacement field would be of the form given here or the form given here, okay. And then we went ahead and derived the torsion equation, which was T by J, where T is a twisting moment or torsional moment, J is a polar moment of inertia, equal to stress by shear stress, magnitude of shear stress by the radial location of the point, equal to your shear modulus times angle of twist per unit length. Okay. This is called as a torsion equation, and we saw how we got that equation in the last class for a closed section, and we worked out a couple of worked out examples wherein we add a member subjected to a end torsion, or we add two step shaft fixed at both the ends subjected to an end torsion. In this lecture we look at what happens for torsion of a open section. Okay. The basic difference is the displacement field. In the displacement field it will not be like what we have assumed before, there will be an out of plane displacement. For example, this sheet of, if this sheet represents a section of the beam or a section of the member, then because of twisting there will not be a displacement just like this, there will be an out of plane displacement like this also. Okay. There will be an out of plane displacement like this also. This being a rectangular section, this will be precisely the out of plane displacement that happens due to warping. Okay. In this course we are not going to look at detailed formulation for warping and things like that, but we will do an approximate analysis. Okay. But we will understand that the displacement field now will change for open sections. For open section, the displacement field is given by u is given by the above expression sigma z E x plus sigma x z E y plus function psi, so function of x and y E z, and this function psi is called as the warping function. Okay. It is called as a warping function, and with this displacement field now you have to solve, find a functional form for psi for various shape of cross sections. In particular we will find that for rectangular sections, rectangular cross sections, we are going to look at rectangular cross section subjected to torsion. Okay. That is, I have a rectangular cross section which is y x, and let us say this distance is w and this distance is t. Okay. Then you can show that the torque would be given by an expression of the form C1 times mu omega w t cube. Okay. And your shear stress maximum shear stress will be given by an expression of the form C2 T by W T square. Okay. where C1 and C2 are constants, which is a function of W by T. C1 and C2 are function of W by T. In particular, if W by T is 1, C1 is 0.141 and C2 is 4.8. If this is 2, it rises to 0.229 and 4.06. If it is 4, this is 0.281 and this is 3.54. If it is 10, it is 0.312 and 3.21. Okay. In particular, if it is infinity, this goes to 1 by 3 and this is 3. Okay. So, now from this expression we will estimate the torque for a given rectangular cross section of a particular dimension to be evaluated by this expression. If you note that what we got before was T equal to, from the previous expression it was mu omega j, the polar moment of inertia. For the in particular it will be mu omega I xx plus I yy, because polar moment of inertia is x square plus y square daz. So, that will be I xx and I yy in particular here. Okay. Then what we will get is, this will for the rectangular section will be mu omega by 12 into Wt cube plus Tw cube. Okay, this will be the polar moment of inertia for this section. Now then if you pull out Wt cube, which is what we have, by 12 Wt cube, you will have 1 plus W by T the whole square there. Okay. So, let us see what happens when W by T is 1. W by T is 1, it will be 1 by 6. 1 by 6 is, this is the torque expression when W by T is equal to 1. From this expression we will get C1 as, from this expression you will get C1 as 2 by 12, which is 1 by 6, which is 0.166. Okay. The value is lesser than that because it warps. Okay. The value of C1 is lesser than that because it is warping. Usually warping will reduce the torque for a given angle of twist. Okay. So, that is what we are observing here. If W by T is 2, C1 would be 5 by 12, which is 0.44, which is 0.416. Okay. So, basically that for 2 it reduces still more drastically. Okay. So, this is what will happen because of warping. Okay. So, having understood this, similarly what we had from the previous expression, tau max would have been T by j into r, okay, where r is the maximum distance from the center of rotation, which is the CG of the cross section, okay, which would be in this case this point A, but the point A has to have 0 shear stress, okay, and that is why this section warps. Okay, there is no continuous flow of shear stress in this section, there can't be continuous flow of shear stress in this section because section A has to have 0 shear stress. Why should the point A have 0 shear stress? It is because there is no complementary shear applied on the respective top and side planes, that is in this cross section there is no shear stress applied here nor here. Okay. So, if I take a section here and look at this sectioned element, there is no complementary shear coming here, this shear is not there. So, there cannot be this shear too. this shear is not there, so this shear also cannot be there. Okay. So, that is why the shear stress at point A has to be 0, which will be satisfied when you have warping of the cross section, and hence the resistance of or the torque required to engender a given angle of twist is lesser when the section warps. Okay. So, having seen that, what is of interest is the case when W by T tends to infinity. You can see it is very close even when it is 10. Okay. So, what we will do is we will assume that W by T is tending to infinity, and in which case the torque would be given by 1 by 3 mu omega W T cube, and the shear stress maximum which is of interest would be given by 3 times torque divided by W T square. Okay. Now, let us apply this to a practical problem. Okay.